Hi, we're going to take a quick look at double angle identities and their use in integration. The double angle identities come from the angle addition identity. Specifically, if I have cosine of x plus y, then the angle addition identity gives me cosine minus sine. And there it is. If I wish to leverage this for the cosine of 2x, then I simply let y equal x in the formula, and I get cosine x times cosine x minus sine x times sine x. And this is our basic double angle identity for cosine. As stated, this is not so helpful. But I can rewrite this with the Pythagorean identity to get what we call the half angle identity for sine, or I can rewrite this with the Pythagorean identity to get the so-called half angle identity for cosine. And just a little bit of algebraic rewriting now shows their utility. If I begin with the fact that cosine 2x is equal to 2 cosine squared x minus 1, I can now add and divide to get an identity for cosine that allows me now to integrate even powers of cosine. So if I have, for example, the integral from 0 to pi of cosine squared x dx, then I can rewrite that as the integral from 0 to pi of 1 plus cosine 2x over 2 dx. And now we go term at a time. The first term is the integral of 1/2 from 0 to pi. And the second term is 1/2 the integral of cosine 2x, also from 0 to pi. This is obviously pi over 2. And this integral right here, because I'm going over one full period of cosine 2x, we get 0. The same kind of reasoning, but a slightly different algebra, can allow us to integrate sine squared x. So if I take my identity here, cosine of 2x equals 1 minus 2 sine squared x. Subtract 1, divide both sides by -2. And you get this guy right here. And so I can integrate sine squared x in much the same way that I can integrate cosine squared x.
Thank you.
Yeah, you're welcome. Since there is a double angle identity for cosine, you might wonder if there's a double angle identity for sine. Of course, there is. And it comes about in the exact same kind of a fashion. So we have sine of x plus y equals sine x cosine y plus cosine x sine y. So that the double angle identity for sine is found by replacing y with x here and getting sine x cosine x plus cosine x sine x. So, now, here's the interesting thing about this. In terms of integration, this integral can actually be done in one of 3 ways. In one way, I could rewrite this using my double angle identity, like so. And integrating with a little bit of repair like so. And we're good. Or I can integrate by using substitution. Let u equal sine x, du is therefore cosine x dx. And so this is integral ready, actually. This is simply 1/2 sine squared x plus c. Or I can integrate by letting, so for the sake of our notes, this is u equals sine x. Over here, I can integrate by letting u equal cosine x. And if I let u equal cosine x, then du is negative sine x dx. So that this is almost integral ready if I repair with a -1, and I get negative 1/2 of cosine squared x plus c. Now here's the great mystery. We know already that antiderivatives must give us the same function with a constant. So that means that all three of these must be the same within a constant. Is that really true? Well, actually, yes, it is. Because if I take this fellow right here and rewrite with the Pythagorean identity, then I can clearly see that this function and this function are the same function within a constant. And if I take this guy right here and rewrite with any one of my double angle identities, such as 2 cosine squared x minus 1, then I can see that this function and this function are the same function within a constant. So that actually my 3 different ways of integrating gave me this 3 different versions of the same constant, plus c. Good. Question? Any other topics? Let's talk convergence, series convergence strategies. Okay. Samantha has a list, and hopefully she'll make that list public for us of all the series convergence tests. Let's just get these on the board. We have the nth term test. We have, what else? Direct and limit comparison, DCT and LCT. Integral test, ratio test, yep. Root test. She's nowhere near him. Integral test. And yes. What other special series have we seen?
The harmonic series.
P series, yep. There's one more special type we didn't see a lot. Occasionally shows up the telescoping series. Yeah. Let me put this over here. Integral ratio and root. Unless I'm missing something, I think this covers it. Okay, now the question is, you're confronted with a random series. How do we proceed? What would you say? What seems like a decent strategy? What would be the principle that you would want to proceed on? Start with any term? Okay. Why? What's the principle that's going to try to lead you there? You used an important word. What was that adverb you used? You can. What was the adverb? You can tell in what manner? She said easily. easily. Yes.
Wait, what?
Yes, our principle here is one of ease or efficiency. We want to go quickly there. So now let's rate these guys in terms of difficulty to use. Which tests are the easiest to use? Interim, geometric, P-series, ratio. If there's something that's easier than that, how about alternating series? Right? And can't you look at a series and say, hey, look at that alternates? Right? Okay. So we're going to put these guys right here in the group of do this first. And we're also going to put, so this is our first tier because they are easy. Then, let's put this guy right here in our second tier, and here's why. The limit comparison test is relatively easy to use because I can use an end model to fairly quickly come up with a good limit comparison. So you remember the one that we had on our on multiple choice, and we wanted to determine converge or diverge here. If I reduce this to its end model, then I can quickly, easily, put somebody famous, determine that this guy right here is comparable with limit comparison to a P-series. So that makes life easy. All right, now we've got 4 tests left. How should we order those? Which are the easiest out of all of these? P-series? We've already covered that. That's in our group 1. That's all in our group 1. Yes. Group 1 covers all of the ones that we can recognize easily or evaluate fairly easily. Okay. You're not getting out of here until you give me some answers.
Yeah.
Ratio test and the root test should really be our group 3. Those are equally easy. After that, the integral test requires a little bit of care and feeding because I have to check the conditions are met, and then I have to actually integrate. And then finally, our direct comparison test. The telescoping over here I have left out. However, it really belongs somewhere in the vicinity of, it's kind of between 1 and 5. And the reason for that is if you recognize it, it's fairly easy to do. If you don't recognize it, it's a little bit tough. It requires partial fractions in order to split apart your terms so that you can see that it telescopes. Does that help? Yep. See you tomorrow.